Yes, so hello everyone. So thank you for the invitation. So my name is Thomas. So I'm a PhD student at LMD in Paris. So my thesis work is about dust lifting and dust storms on Mars. But today I will talk about this. We'll talk about a previous work that I've done also on dust on Mars as a research engineer. So, which is about the power attenuation of Martian rovers and lander solar panel due to dust deposition. I put you here a little picture of inside solar panel covered by dust, or at the beginning of the mission and at the end of the mission. So you know that the mission died because of the dust on the solar panel, and there was no more electrical power for the mission. So it is really important to know the available power produced by the solar panel for future missions. And so there were already several studies that have been conducted on this. Studying some empirical model or theoretical model. But one which works pretty well is the one explained in the article of Lawrence and collaborators in 2021, which is a simple model, an empirical one, using a simple attenuation factor of 0.28% per sol. So I show you here the model in red and in black the measurements of the electrical current measured by two different landers, so InSight and Curiosity. So you see that this model sometimes works well. For example, for InSight, during the first 800 sols, it worked pretty nice. But for example, for Curiosity, you see that the decrease, even if there are some dust cleaning events, the decrease is not always 0.28% per sol. So it doesn't work every time, and also it's totally empirical model and it's not very physical. So what we tried in my laboratory is to find a model which is more physical and describe better how the attenuation is done by the dust on the solar panel or on every surface. So this new model that I worked on, we integrated it in an existing model, which is called the LMD 1D thermal model. So it's a one-dimension model, radiative convective model, but it's derived from a full 3D general circulation model, which is now called the planetary climate model at our laboratory. And so this model has the advantage of working really fast. So you just put some inputs so the user just choose some inputs. So the time where he wants to start the simulation, the location, the duration of the simulation. Also some other important input like the surface pressure, the bare ground albedo, the thermal inertia. And also it has the user has the possibility with my new dust deposition model included in the LMD1D model to choose the slope, inclination, and orientation as an input. So that will be very important because the solar flux will not be the same and the attenuation will not be the same whether the solar panel is inclined or not. And also the dust optical depth, you can choose one value, or you can follow a scenario that I will talk about later. So you have several outputs in this model. So you have all fluxes, so solar fluxes and infrared thermal fluxes, temperature, of course, atmospheric temperature at the altitude that you choose. And what we are interested in is the dust deposition rate on flat surface and the solar flux received by a surface covered by the dust at this dust deposition rate, which can be inclined and oriented as the value the user wants. And you have also access at the output of the visible extinction opacity. So as I said, so in input, you need to choose the dust optical depth. So either you choose one value, or you can follow some scenario which are derived from measurement from thermal emission spectrometer in Mars Global Surveyor or Mars Climate Sounder for more recent missions aboard Mars Reconnaissance Orbiter. And so we have a value of the dust optical depth in the infrared in absorption at every location on Mars at every time. So we have one value per sol. And you have this scenario for each Martian year, from Martian year 24 to Martian year today, which is Martian year 36. And so you can choose the Martian year, so either a classic Martian year or a Martian year with the dust storms, global dust storms. And you can either choose one specific Martian year, or you can also choose to use what we call the climatology scenario. So in this scenario, we average all the Martian year of the dust optical depth of all the Martian year, removing all the global dust storms, and we get one classic Martian year of dust optical depth. So you can use this scenario, or you can use what we call the warm scenario. So in this case, instead of averaging all the Martian years, what we do is that at each date and at each location, we take the maximum value of the dust optical depth, and we increase it again by 50%. So to make extreme but still realistic scenario. And we do the same for what we call the cold scenario, but instead of taking the maximum value at each location and each date, we take the minimum value of all the Martian years, and we decrease it by 50%. So to let it realistic but still extreme scenario. And then in the model, we need to calculate the dust deposition rate, and we'll use the dust opacity from the scenario. So the first thing, so the dust deposition rate is calculated with this equation. And that depends first on the Stokes speed, which is the speed at which the dust particle will fall on the surface, on the solar panel, for example. And so the Stokes speed is this equation, but it depends of two important parameters. So the first one is the average particle radius. So what we do is that we assume a distribution of dust particle size, a normal distribution. And so we have two parameters, the effective radius of the particles and the variance, the effective variance of the particle. And so that gives us the average particle radius, which gives us the Stokes speed. And so we have some measurement about this radius. And so near the surface, what we choose is to put the effective radius of dust particle in the atmosphere to 2 micrometers. But the other parameters, beta here, is the sphericity coefficient. So it tells us that if our particle is spherical or not. So the closest is to 1, the more spherical is the particle. And so we have a lot of incertitude on this coefficient, and so we can tune it to fit the best the observation with our model. And so the value that gives us the best agreement is 0.5. And the second element of the dust deposition of the dust deposition rate is also we need to compute the mass mixing ratio of the dust particles. So what we assume is that the dust is well mixed in the atmosphere, at least in the planetary boundary layer, and so we can assume that the mass mixing ratio of the dust near the surface is function of the column dust opacity, which we will derive from the dust scenario that I talked before. So So this is the dust opacity of the scenario, but converted in the visible, so in extinction. So we need to convert it first because the scenarios are in absorption in infrared at 9.3 micrometers. So we need to convert it in absorption, in extinction, sorry. So we need to convert it in absorption first, and then to convert it in the visible. And so we use 2.6, so 2 times 1.3 coefficient, so 2.6. And this value is the one that corresponds to an effective radius of 2 micrometers. So that's why we use this value, but of course it depends on the size of the particles. And then once we have so the mass mixing ratio and the Stokes split, we can compute the dust deposition rate and integrate it at each time step to get the amount of dust that has accumulated on the surface from the beginning of the simulation. Once we have the amount of dust that has accumulated on the surface, on the solar panel, we need to calculate how much it will reduce the solar fluxes. So first, we need to calculate the attenuation by the atmosphere, of course, so of the solar flux. So we use the model of Spiegel-Forget 2008, which allows us to calculate the solar flux on the slope. And then once we have this solar flux, which is reduced by the atmosphere, we have the incident solar flux on the dust layer, which we know the amount of dust. And we use to calculate the attenuation, the two-stream multiple scattering scheme from Thun et al. 1989. And this model is actually the model we use to calculate the attenuation in the atmosphere. And here we use it to calculate the attenuation by the accumulated dust on the solar panel. So this model takes as input the single scattering albedo, the asymmetry parameter, the solar zenith angle, and what actually characterizes the surface on which we calculate the solar flux, which is the albedo of the solar panel. And it's the only parameter that characterizes the surface on which we calculate the solar fluxes received. It's the albedo of the solar panel. And we also need the dust optical depth of the accumulated dust layer on the panel. And this we can compute it using this equation, since we know the amount of dust in kilograms that are per unit of surface that has accumulated on the panel. And so, of course, this dust opacity here of the accumulated dust depends on the radius of the particle that have accumulated on the panel. And actually, this radius here is not really the same than the one of the particle in the atmosphere, because of the aggregation of the particles once they are deposited on the panel. And so the radius of the particle in the atmosphere will not be the same than the radius of the accumulated dust particles. And so to model this aggregation of dust particle, what we do is that we say that the more dust particle we have on the panel, the bigger the particle can be because of the aggregation. And so what we do is that we take a linear function of the mass of the dust accumulated on the panel to describe the radius of the particles on the accumulated dust. And so we have this coefficient here of linearity, and we can calculate it to fit the best the observation. And the observation we used is the observation from the lander InSight, because the InSight has the advantage that there were not much dust cleaning events, so it's not an advantage for the mission, but it's an advantage to compare it with the model, because it doesn't it doesn't simulate the dust cleaning events. And also, it also has the advantage that here, what is shown here is the real current in ampere that is measured by the solar panel of the lander, which I will tell you later, but it's not, we don't have access to this value for other mission. We have access to another parameter, another field that is not really relevant, but for InSight, we have the electrical power. And so we can compare it to our model. So in red here, you have the model I just described. And in blue and black dots, it's the measurements of InSight solar panels. And so, of course, we use the right scenario. So from Martian year 34 to Martian 36 to describe, to make the right comparison. So what you see is that sometimes the electric current goes back up. So this is the effect of the Mars getting closer to the sun. And sometimes you have a big gap due to regional dust storm or bigger dust storms. And for example, here you have dust storms at the end of Martian year 34. And you see that here, the current goes back up faster in the model than in the measurements. So this is due to the fact that we use the dust opacity scenario. And okay, so we use this dust opacity scenario, and it differs to the dust opacity, which is measured by InSight. So first, you see that here the dust storms is shorter in the scenario, and here it decreases slower in the measurement of InSight. So that explains why you have here this discrepancy here between the model and the observation. So that's the first thing. And you can see also that there is a gap between here, the scenario, the dust opacity scenario, and the opacity measured by InSight. So this is well, we think that this is due maybe to well, first, that might be due to the fact that the dust scenario is measured by orbiter, and this is and this opacity here is measured by lander InSight. So it's two different methods. And also here it's just the opacity of the dust, whether here it's supposed to be the opacity of the atmosphere. So it includes also water ice clouds. So that might explain also the gap between the two, the opacity of the water ice clouds. So for InSight, we have high resolution temporal measurements, so you can also compare for other local times, because this comparison here is the maximum daily current every day. So what I show basically is the current measured around noon. But you can also look at other local times at the afternoon or during the morning, and see if the model reflects well the cycle. And so that is the case. So we have a good agreement between the two. And what I show here, so this is the comparison for another mission, so Mars exploration rover mission, so first Spirit. So as I said before, here we don't have access to the electrical current of the solar panel of the mission. We have only access here to what is called the dust factor. So it is actually the incident solar flux above the dust layer that has accumulated on the surface. No, sorry, it's the solar flux received by the surface divided by the solar flux above the accumulated dust. So it's basically the attenuation due to the dust. But the problem is, of course, is that what we really measured is what is called phi panel here, is the incident solar flux on the panel. And we don't have access to the solar flux above the dust layer that has accumulated. So this dust factor depends on this flux, and this flux must depend on a model on which we don't have access to the details, and which must calculate the attenuation of the atmosphere. And so this is actually not really an observational data, but a semi-observational, semi-theoretical data. And so that's why the comparison is less relevant than the one we have with InSight, but still interesting to compare it with the model. And so here, so in red, still the model, and in black, the observation. So what we see is that we have several dust cleaning events. And as I said before, so the model doesn't simulate the dust cleaning event. So you have to relaunch a new simulation at each time and put the amount of dust numerically that correspond to the right dust factor at the beginning of the simulation. And you have to relaunch simulation every time you have a dust cleaning event. So what you see is that we have a good agreement, especially at the beginning, but indeed the model little underestimate the dust factor at some point, but still good agreement overall. Same for opportunity. We have a good agreement overall with a lot of dust cleaning events. Another comparison here is the comparison with the Pathfinder mission. So the Pathfinder mission occurred in Martian year 23, but there were no measurements at these dates of the dust optical depth. So what we know is that, so we have no scenario for Martian year 23, but we know that this Martian year was a very dusty year. And so instead of using the right scenario, because we don't have it, we use Martian year 27, which was also a very dusty year. So to try to have the better dust optical depth that were during the mission. And we still have a good agreement, but we see that in the measurement also there sometimes we have a gap with the model, and sometimes the measurement goes back up, and so maybe that's this discrepancy can be due to the fact that all the measurements were not necessarily done at noon, but maybe at some other local times near noon, and also the fact that it depends on the incident solar flux above the dust layer, which might be miscalculating the attenuation of the atmosphere. So last comparison is with Phoenix data. So here we have the right scenario to use. But if you look at the beginning of the mission, you see that I won't start the simulation with a dust factor of 1, because in the paper of Drup 2010, they explained that during the landing, the spacecraft lifted dust in the atmosphere and reposited it on the panel, and so that made a lot of dust just at the beginning of the mission on the panel. And you see there is this big decrease at the beginning of the year, which is due to the opacity here in black, which was measured by Phoenix, that were very high, which is not the case in the scenario. So that's why you have this decrease, the important decrease at the beginning, and not a big decrease in the scenario. And you see at the end that we have here a gap that is increasing during time at the end of the mission, and so that is assumed maybe to be also due to maybe the miscalculating of the solar flux incident, or maybe also the model that is not really good, or maybe just this is due to a dust cleaning event that we don't simulate. So of course, so this is the dust opacity measured by Phoenix compared to the scenario. So you see here at the beginning of the mission, I showed you before. And as a conclusion, so I would say that this model is a good tool for future mission because well, it allows to gives you the solar flux received by any surface which with the orientation and inclination you want. So it's a good tool for future mission, especially that it's a very pessimistic model because it says that it calculates if there were no dust spinning events. So it's better to assume this case than the other way. And the comparison with all the mission are satisfying, especially the one with InSight, which is the most relevant because we have access to the electrical current. And I think that if we have access in the future to the Mars exploration rovers mission current in electrical current, the comparison will be much more relevant. Will be better to test our model. So we'll see in the future. So thank you very much. If you have any questions, yes.
I guess I have a comment and a question. Earlier on, one of your first slides, you show that you use the Stokes drag equation. Yeah. In fact, the particles that you're using, 2 microns,
Yes.
they're smaller than the scattering length between molecules on Mars. So you should actually use the molecular scattering regime equation of Epstein.
Okay.
It's in the transition between the two. I think the scattering length is about 7 microns at the surface of Mars. So your particle is smaller than the distance between the molecules. Yeah, so officially the Stokes drag doesn't work anymore down there. They will fall faster than they should do.
Okay.
According to
that's
Stokes.
good to know because that's the equation we used in also in our 3D model. So
you should work out what's called the Knudsen number, which is the ratio between the scattering length and the size of the grain. And if it's bigger than 1, then you should use the molecular drag equation. It's super simple. It's easier to use than the so yeah, then I guess you adjust it then with the beta, which maybe that makes it all right again. I don't know, but
for the beta,
yeah.
well,
that's just an empirical thing.
We don't have it's a parameter with a lot of incertitude. So because of course the particles in reality are not spherical, so we just put it's a simple way to modelize the fact that they are not spherical. But
anyway, I can give you a reference to the Epstein equation if you.
Okay. Yeah.
My question, I guess, is there were observed several vortices at the InSight landing site, but as far as I remember, none of them had any dust in, which is weird.
Yeah, so
they're like dust devils without the dust in.
Yeah, InSight measured some pressure drop and vortices, but it never removed the dust on the panel.
So nobody knows why still, or
I don't know. Yes.
No, I don't think there is an answer yet. Yeah. So that's interesting. Thanks.
I think one hypothesis was about the size of these vortices, but it was an hypothesis. I mean, nobody has a final answer, right? Yeah, maybe. They weren't able to do this as well. In fact, since I have a mic, may I ask you a question about this accumulation? You were talking about a linear model to aggregate the dust. I wonder, are there laboratory results from this project that could help to make this dust aggregation model more accurate?
Yeah, this is the simplest model we could do. So we saw that if we use a constant effective radius for dust particles in the dust layer, so you have a discrepancy that appear here during the mission. And so if you make the particle bigger and bigger during the mission, meaning it's due to aggregation, then you have the right fit. But yeah, it seems that if you use a constant effective radius, then the current decreases too fast, because making the effective radius bigger decrease the opacity of the accumulated dust layer.
So you measure peak current. Do you have any information about if the solar panels, the efficiency of them reduces over time or anything like that? Do you include that in the model?
No, we don't include that in the model. What's the only characteristic that simulate the panel is the albedo of the panel, and we keep it constant in the model. But I think that the decrease of the efficiency of the panel is negligible in regards of the dust that accumulated on it. I mean, the decrease of the current is due mostly to the dust and not the efficiency, I guess.
Yeah,
of the panel. Maybe it's more important than I think. I don't know.
The question is because here you're using current, the others you're using a ratio.
Yes.
Presumably whoever made the ratio, the engineers have included potentially some model of the reduction of efficiency in the solar panels for the other rovers. But you're using the raw data here, so maybe it's, I'm just wondering if there's a slight difference due to that between the results here and the results of the other missions. Because there's two solar panels, and you see the blue and the black, 10-15% different, maybe.
Well, maybe sometimes it's also due to the shadow or things like this, because they are not at the same position.
Yeah.
Or the efficiency, I don't know.
Yeah, you talk about the radius and these things. Do you make any assumption of the size distribution in the atmosphere, log normal or?
Yeah, we assume log normal distribution is 2 micrometers effective radius and a variance of an effective radius of 0.5.
Yeah, have you investigated if the size distribution changes with climatology, with dust seasons and things?
Well, this has been studied a lot, and it seems that the log normal distribution is the right one, and it works well. It works at the same if you use a lot of bins with different radius for particles. So seems to model pretty well the size of the particle, this distribution.
Hi. If you take away your rover and your solar panels, then one part of your work is essentially depositing dust on the surface. So aren't there other works already who did this, calculating how much dust you actually accumulate over a certain time on the surface? Something to compare with? Or the other way
there are other models that calculate the dust deposition rate. They don't calculate the mass of that has accumulated. Well, some model does because they are studying the available dust on the surface to be lifted. But yeah, there are some other models that calculate the speed at which the dust particle falls. But I haven't made a comparison with this model, but they essentially based on the same equation than than this model. Just for example, in most general circulation model, for example, you use this equation, but instead of using a constant effective radius, then the effective radius become 4D fields, like depending on time and space. But we used only an average value of what the particle size should be near the surface. But I don't have any comparison here between my dust deposition rates and this model and other models. But yeah, that could be done. Yes, that's right.
I would also support John's point that you should at least add a Cunningham correction factor to this or so. It kind of triggers you if you pressure range.
Any other question? There is still a question.
Just have a comment that in experiments, you normally do see aggregates forming on the surface. So it's not just on Mars, but I don't know of any work which actually tried to quantify it. I just know that it happens. Yeah.